Hello, hello, hello. This time around I'm going to do a Grasshopper tutorial. So we're taking a break from our Blender stuff. And I'm going to show you how I do water flow analysis, and maybe we'll make something nice out of it as well. And to do that, actually let me just run Grasshopper while I'm talking. To do that, I need some sort of a form, right? So something for the water to flow against. And in this case, like for this example, I'll just use a regular planar surface. So I'll just type in plane, starting from 0. And let's just say I'm kind of eyeballing it. Let's just say it's this big. So just a regular flat surface. And of course, it's right now quite boring, so let's amp it up a bit. Let's make it a bit more spicy. So I'll rebuild it with a few more points, like 5 by 5 points, just to get more resolution out of it. And then if I turn on, if I go to points on, I can mess around with these control points and kind of move them up and down as I please. So I'll just be creating some sort of a irregular landscape surface. I will not be going too heavy on this. Maybe this one can dip a bit more, because this is just, to test out our ideas and to see if they work or not. So let's say we have our landscape, right? And I'll show you how to do it with a mesh or with a poly surface or whatnot. But for now, just a single surface landscape. I'll reference it into Grasshopper as an SRF, as a surface. Right click, set one surface, hide the one that we have in Rhino. Yay, we have a surface in Grasshopper. So now to start things off with, we need a logic, right, on how to do this. There are plugins that do water flow analysis, but I think it's such a simple thing to do that you don't really need a plugin for that. Well, except Anemone, which creates a loop so that we can animate the water flow. But other than that, no plugins are needed. So logic, right? How are we going to proceed? So I'm thinking of having starting points, a grid of starting points. So I'll just divide. That's not how you divide. Divide surface. I'll just divide it by, let's say, 15 by 15. So I'll just create a slider, plug in 15 to U and V, and now we have, well, actually we have 16 by 16 points because we have 15 divisions. I always explain this, but I think it's an important one. For instance, if we have 2 by 2 divisions, right? 1, 2, 3, 4, right? In total, we have 4 patches, but we do have 3 by 3, a grid of 3 by 3 points, right? So it's always going to give you one extra point, like this surface divide tool is going to give you one extra point, depending on what kind of a number you plug in here. So 15 will give me 16 points, but we don't care about that. Another thing is that here, if I were to, let's go for param viewer, just to show you. If we were to check it with a param viewer, I can see that it's creating a data structure. And that data structure is basically every column or every row of these points is in a separate data branch, right? So that it just structures it that way. We don't need a data structure here, so we want everything to be in a single list. So I'll just right click on the P output, point output, and flatten it out. So now all of the points live happily in a single list. Now it's time to move them somehow along the surface as if they were droplets of water flowing down, right, in the surface. And to do that, it's actually pretty simple, but before we continue on, I need to draw it out for you. So let's say that's this is a section of our of our landscape, right? And let's say I have a droplet of water, which is very small, but there we go. I have a droplet of water which is here. So how do we simulate how that droplet will flow along this landscape? Well, it's quite easy to do. If we were to move it down by some amount, doesn't matter what kind of amount, but if we were to move it down to here, right, then we have another version of that droplet, which is going to be here, and then we project it back to the surface according to the closest point. So we find the closest point on the surface from this blue point here, which was moved from the, from its initial position. So we end up getting something that is like that, right? So let me grab a green color. We end up getting a point here, right? So we just moved it down and projected it back as a closest point. And now I can continue doing this, right? I can move it down again by the same amount and project it back, right? So now it's here. And move it down, project it back, move it down, project it back, move it down, project, blah, blah, blah. So it's always going to flow downwards. It's always going to find the direction at which it should flow downwards, right? And this can happen for every point. So let's do that in Rhino. If I grab these points, and actually I will want this to be animated, right? So it just doesn't move once. So I will actually create a loop, start, that, and loop end. So again, the plugin that does this is called Anemone, and it's on Food for Rhino, so you just can get it from there. Loop start and loop end always connects with this dashed line. That I will not be explaining how it works. I've done that in various tutorials all throughout. But the basics is this is where we plug in how many times we're going to repeat that process of moving down, projecting back, moving down, projecting back. So I'm just going to say for now 101, whatever, some number. 101 is fine. Second input for loop start is a trigger, which is just a button. Every time when we want the simulation to restart, we just press the button, right, and it will restart. And third one is the data to loop. So the data to loop is going to be our points, right? So we're going to kind of keep updating our points in this simulation. Okay, we have that set up. And now if I actually were to connect it like so, it would just, the points are not being moved, nothing is happening with them. They just kind of keep repeating. Like points, 101 times, right? So it just kind of keeps repeating those points. Sure, cool, but we kind of want some movement, so I'll just disconnect it here. To get movement, well, we move things, right? So we just use the move tool, and we will move those points, and now they're moving up by, I believe it's 10. Yes, they're moving up by 10. But I will be moving them downwards, so I will be creating a z vector, unit z, and actually I'll plug it in like so. So now it's still moving up, but by 1 unit. And for this z vector, I want a negative value, right? So I'll create a negative node, plug it into z, and now this node is waiting for me to give it some value, basically by how much, how long is this red arrow, how much down are we moving these points. So I'll just say, how big is our landscape, by the way? I'll just say 0.5. I don't know. If we need more precision, we will just decrease this value so that the points are being moved much less. So now you can see the points are being moved, and actually if I plugged in the moved points and then run the simulation, you know, they just kind of fall. So that's boring. We don't want that to happen. We want them not just to fall, but actually every time when they get moved down, they should be projected back on the surface. And a tool that does that is called surface CP, surface closest point. This guy. Okay, so it has two inputs. First one is what, you know, the points to search from. So that's the points that are we moving down. In this case, the blue point here, right? And also it asks us for the surface to project it back to. So I just grab the surface from the start of our definition and just kind of project it back like so. Now the wiring is all messed up. Let me try and kind of make it nicer a bit. There we go. So now they're not just being moved down, but they're being projected back, and we get the closest point output here, which we can connect to loop end, like so. And you can already see how everything is flowing into one convergence point. And that's because I created this landscape to have this kind of a dip. I've hidden everything except the loop end and the surface, and now I'm going to repeat it so that you can see better. And that's how they do it, right? Wonder why these are not flowing inward. Oh, they have a small bend here. That's fine. We'll have them like that, or maybe not. Let me show selected. Grab that surface. Points on, points on, and I'll just do a little bit of, there we go, so that will flow there. And these ones, maybe we can do this. And maybe we also want these 2 points to go down like that, even more, like that. There we go, something like this. I'll hide the surface again. So now there is a problem. You know, we only see the points. You know, it's cool and all, but we kind of want to see a bit more, right? So I'm going to right-click on the loop end here and choose to record data so that it records every iteration of the loop as it's doing the loop, right? If I run it now, you can see that all of the points are being recorded. You know, so we already can start seeing their path. That edge right there, I don't enjoy it. Let me show selected, points on, and I'll just grab some control points here, move them up like that. So now that edge is fixed. Okay, so our points are moving, they're doing great. Let's build a curve from them. So the problem is that if I were to just say, you know, oh, cool, I get a bunch of points from here, you know, a crap ton of points. Can I just do polyline through them? And technically, yes, I can, but the problem with it is that it will draw, actually, let's have repetition set to 0 and just show you this way. It will draw a polyline through the whole damn thing, right? Through every iteration. So if I have repetition set to 1, you know, it does this and so on, right? So it interpolates a polyline through every given iteration, and not the way we want it to be interpolated. It's quite easy to fix it. To do that, I just need to flip matrix, right? So that every point from iteration 1, or rather every index from every iteration, is placed in the same branch, right? So if I were to, actually I can do this, point list. I wonder if this is gonna crash my computer. No, it's not. 1. Well, maybe a little bit less. 0.2. Plug that one in. Okay. Let's zoom in. Somehow. It's gonna take a while, it's a lot, but you can see that the indices of these points are the same, right? So what flip matrix will do is it will take all of the points with the same index and it will place them in the same branch, meaning that if I flip matrix and then use polyline, it generates a very clean polyline for me, just like that. Let me hide the surface, just like that. So we're getting there, as you can see, right? It's going to be complaining a bit that zero length segment was collapsed, but that is absolutely fine. It means that sometimes the points don't move if they find a resting position, right? If they reach the end. And it definitely becomes the case if we run the simulation for longer. But we end up with something like this. Let's do 196 iterations. No, that's way too much. 150 should be fine. So I'll just wait for it to finish calculating, and actually let me grab a panel and connect it here just to see when it's gonna finish. Come on, go, go, go. There we go. So this is done, right? And we get our flow, surface or landscape flow, water flow analysis. There are a few things to fix here. First one is this polyline curve. What we can do with it is we can first say that all points that are in the same position should be cleaned off, should be collapsed or welded into one point, right? So there are no duplicates. And if I just type in duplicate, remove duplicate points, plug those in here, plug in the output to my polyline, it should be much cleaner now. All right, we have that going on. I'll flatten the list of polylines, and I can see that in the list I have a few nulls, right? A few null polylines. So I'll be fixing those. To fix that, all you need to do is just use clean tree component, plug that one in here, and now if I grab a panel and check, there are no polylines, no nulls here left. Okay, so we have that done. The thing is, well, it's not necessarily a thing, but I really hate just analysis without actually producing a form or anything like that. While this one looks really nice graphically, it's not a form, it's not a shape or anything like that. So I started thinking, how can we, what could be another use for this? And the reality is that you can do just like water flow analysis is used to kind of see how water would flow along the surface. It's also how stresses flow along the surface, right? From dead load stresses, how they flow along the surface from the top, from the highest point of the surface to the lowest. Meaning that if we were to thicken these parts, we would make a very rigid shell. We could make the shell quite more rigid as if it was without these thickened lines. So I'm going to do that, and also it will look cool. So that's the main reason actually. The next step is going to be quite heavy, so I'll just create a data dam, just like that, data dam. And actually I'll press play for now. And for this particular thickening, pipe will just destroy your calculation times. So I'll use a plugin that's called Dendro. You can also use Cocoon, that's fine as well, but Dendro seems to be just faster, so might as well use that one. Also, I haven't used Dendro for a while, so it's going to be a good, it's going to be good to remember how to actually use it. So in Dendro, I will choose to create a volume from a curve. So curve to volume. I'll plug that one in here. Then curve radius, I will need to specify a radius. I think like, let's start with 0.5 and then we'll reduce it if we need to. Whoops. We'll reduce it if we need to. And the last one is settings for creating the volume. So under convert, there is this create settings toolbox here. I'll plug that one in here. And it's still complaining. What does it say? Radius must be at least 33% larger than the voxel size. So the first input here is the voxel size, and it's 1, and our radius is 0.5, so of course it's not larger. So we need a voxel size of like 0.3 for this to work. Cool, immediately starts working. That's nice, that's always nice to see. Even though it immediately starts working, this is not something that I wanna, not something that I find very aesthetically pleasing. It's just a bunch of noodles. So I'll reduce the curve radius to 0.3 and the voxel size to 0.2, I guess. Or even less, 0.1. As you can see, it starts taking a while to calculate. And maybe curve radius 0.2. Oh, this is much nicer. Okay, so we have this going on, and this is already a pretty nice looking form, but the problem is that the output of it is Dendro volume, which is neither a mesh nor nothing even similar to that. So we need to actually convert it into a mesh, and I'll go to volume to mesh. I'll go to convert tab under Dendro, go to volume to mesh, choose that one. Volume goes into volume input, settings go into settings input. And I have my mesh volume output. And this one should be a mesh. And it is. Super. There is a few more things that I want to change here. For instance, I will probably go for smooth volume setting tool. And I will plug it in between the volume from curve and mesh from volume right here, where I can change the width, the type, and so on, a bunch of things. I will not be messing around with those too much. I think the default values work quite well. It just smooths out our output. So now that's a mesh. I can bake it out, default, okay. Move it here. Let's go for Arctic view just to see how it looks like. Seems to be quite clean. And you can, reapply it on any kind of surface and have a structural bracing system. Okay, so when I have something like this done, I always start thinking about different applications and different ways of how I can work with this. So first things first. set one surface right here, like that. So that works, and now for points I will just divide it up. Let's keep it simple. Like that, like that. Plug it in here. Definitely not 100 by 100. Let's start with something simpler. 16 by 16. Something like that. Why are you red? You are red because this is not flattened. Okay, there we go. Reset. Look at the pretty curves. Definitely want more. So I'll do 25. And I'll just wait for it to finish up, and then I'll finish my tutorial with that. Okay. Actually, come on, go 120, 130. This kind of crap is really slow on Grasshopper. Ah, there we go. Press play. Do the thing. Okay, look at the preview. Invalid mesh, come on, I don't have the time for this. Can we just have it without smoothing? Can you just work without smoothing? Yes, you can, so screw smoothing, we don't care. We end up with having something as lovely as this, which I find quite pleasing. Let's see how it looks like in Arctic view. There we go. And that is that, I believe. So I hope you enjoyed it, and we will continue working with some swarms and some more points floating about, and then creating forms in probably the next video. Bye.